All right, now that we've learnt some of the things that are to be learned about solvers, let's go ahead and use one that's made for us. The wonderful thing with Bifrost is that most of it's solver-based stuff. Particles, it's smoke and fire, even NPM, which we're going to get to in a couple of weeks. They all look really similar, and that's a really, really good thing. So let's get started by having a look at this wonderful plant here that Ying's provided for us. We'll just check out our outliner as we do. So this is geometry, 2 spheres and a carnivorous plant. So as always, we'll hide that, create the graph, and I could bring all 3 of those in at once if I wanted to, but what I want to do just now is I just want to bring in the carnivorous plant because that's what we're going to use for our particles. So let's have a look at our plant. There we are, we've lost its eyes. And we've lost most of its smoothing and stuff like that, but that's okay because we're just going to use this inside of Bifrost to generate our particles when what we're going to display is the mesh itself. So here's our plant. Let's start by adding some particles to it. The quickest and easiest way to get particles ready is just use the basic particle graph. This comes in, looks a little bit daunting in that it's got no inputs and outputs. It's got nothing there. You'll find these all over Bifrost. They are a starter pack for you, really. All you have to do is right click on them and explode them. Here's our simulation engine, here's our source, here's our collider, and here's our particle solver settings. First thing we're going to do is we're going to make some particles. So right now nothing's going to happen because the particles have no source. So let's go ahead and create a mesh sphere. Now what's going to be pretty good for this sphere is if we should probably take a look at it. It's going to turn up there at the origin. What I'm going to do is emit particles from the sphere. So what I'm going to need to do is put the sphere into the mouth of this plant. I could use the transform points and all that, but it's probably easier just to use the position and the radius on the sphere node. So if I just move that so it looks a little more centered and then move it up somewhere like that. It's looking pretty good. And then just bring the radius down. Move it forward a little bit, radius down a bit more, drop it down a smidgen. So there we go. We have a sphere in the mouth of our plant. So we've done that. We can pop that into the source particles. We can pop a terminal in to look at our particles. And let's just hit play. So here we have a bunch of particles. Let's break those connections for now. We'll just take our plant, put them up here. Don't need an input. What's actually happening is the sphere is emitting a ton of particles, just like it says on the box, you know, basic particles. To make this a little more reasonable and believable, we're going to need to essentially collide the particles with the plant. So what we're going for is the plant shooting spores or something out of its mouth, right? So we'll just plug this into the collider and reset the solver by going back to 0. And let's have a look at some things at the same time. So we'll put in another terminal and we'll drop our plant in there. There it is. And we can drop our sphere in there later if we want to, but let's have a look at what happens now. So you can see that the particles are being created and they're colliding with this mesh. They're not falling through the mesh anymore. They're filling up the inside of the mouth and just rolling out. Just like that. Great. We've just made our first particle system. So what now? Well, that was easy. What about having it shoot out of the mouth rather than just slowly dribble out like it's doing at the moment? So this is where the source particles comes in. We're going to talk about what we need to do for these. This is going to control an awful lot of the particle system that we're seeing, right? So we'll start off at the beginning. Are they on or off? Right now they're off. They're disabled. There's nothing going on. You've got a start frame. When do they start? Well, they start on frame 1. We can change that and say don't start until frame 25. And we press play, nothing happens, and then 25, off they go. It's all pretty self-explanatory. You can use an end frame so that they only emit for a certain number of frames. Like that. Great. You can talk about how they're created. So these are being distributed over a surface, but they could be generated in a volume as well. And then you've got a volume detail size. Then we get to rate. And that's the number of particles emitted per step of the simulation. Now, simulation steps are another thing. Every time you change frame, you're starting a new simulation step. If I change this rate here to something like 2, very many less particles. It's only emitting 2 per frame. What we had it on was 100, so we can go anywhere between there. 25 will give us a few more. Now if we go back to where we were, that's what 100 per frame looks like, or 100 per step. The steps don't have to be frames. 3 ways of changing our rate. So right now, when this is set to count, we're counting, this is the count, this number per frame. We can change it to density. You get a lot more particles that way because if you check the info here, number of particles per frame is based on the world space unit area for surface distribution and unit volume for volume distribution. So we're on surface distribution. If I just plug in my sphere, so what it's saying there is it's 100 particles per the surface area. So the larger the object, the more particles are emitted, more or less. So just to give you an example, we'll leave everything the same, but I'm going to take this sphere down to a much smaller size. We'll leave our source particles on surface and density. You can see there's many, many less particles in there than, for example, when our sphere was, I think about 0.4. Many, many more particles. So that's how that works. Then you've got count per point, where if you're emitting particles per points, or if you have an object, it's going to emit this number of particles per point in the object. Then we get into our particle properties. So what we've got to start with here is speed. How fast are the particles going? If I set this to 0.2, you can see that the particles aren't coming out as far before they're flying. Now we have gravity on right now, which is why they're all falling out, falling down. We'll get to that in a minute. But this is the speed at which they're emitted. You can change the direction of the particle emission as well. So if I say emit along the Z axis, then they're thrown out further before they start feeling the effects of gravity. Normal speed is the speed along the normal direction of the source geometry. So if I change this up to 10, they should fly out from the sphere really quite fast. There we go. Yep. Let's get this back to 1. Spread, this is how far the particles spread out along the direction. So when this is set to 0, they're essentially going to go straight along the direction. So if I set it to 0.5, it would spread it randomly around 180 degrees, basically. And 0.2 is all right. Inherent velocity is if your object is moving when you emit the particles from it, does it inherit any of that velocity? Bounciness we'll get to in a minute when we talk about friction and stuff. Live forever is explanational. So you've got an age. At the moment it's 2, that's 2 seconds. So if I set this to 49, which is 1 frame shy of 2 seconds, and use end frame, leave this set to 2, then what we should get is pretty much all of the particles dying. There we go. Because they're only living for 2 seconds. If I set this to 1, and wait for it, then they die a lot faster. You see them just pop out of existence there. So the age limit is how long they live in seconds. So we'll set that to 10. If you've got live forever on, they just won't die unless you tell them to die. And then the size is the size of the particle. So if I say 0.05, much smaller particles. Pretty self-explanatory. Pretty good. These are of course the basics. And what I'm going to do just to make life a little bit nicer is I'm just going to give this a color. Like that. We'll change this over to a float 3 and we'll just get 1, bang. Reset the solver, play it again, then we've got yellow. Pollen, if you like. So those are the source particle settings, okay? So that's what you're doing to the particles as they are born. You've also got solver settings, and these are the settings for the solver itself. The important ones here are gravity. First off, let's kill the gravity. You can just switch that off like that, or you can do what we're going to do in 0, 0, 0, the gravity. Now the points don't fall down. They just go out along their vector and their bounce vector because they are colliding with the object. Then we're going to take a look at viscosity. What viscosity does is basically this number is the resistance to deformation of the particles. So if I turn that up to say 1 and press play, you see that it's a bit slower, but they're also not spreading out as much. So they're resisting deformation. I'll leave that at 0 for now. You've got a lot of other solver settings in here that you can work with as well. So you can change things like I want my particles to be cubes, not quads. We'll take that back to the beginning, and I might just drop my rate a little bit. Again, you know, take that back to count. Just learn from watching me do it as well as what you've done yourself, and we'll play that. You can see that they're cubes now. All good. So that's one other thing you can do there. Numeric property is if you wanted to show numbers off there. You've got all of your collision options, which this is already colliding. So these options apply to the collider setup, and the colliders have their own options as well. So we'll get to the colliders in a minute, but solver settings will let you control this kind of thing overall. So you can have self-collisions. Do the particles collide with each other? Yes, they do, and they're bouncing around all over the place. Do you want them to spin on collision? Yeah, you can see them spinning away there. How much do they spin? Again, viscosity. How resistant are they to deformation? Store self-collisions and store surface collisions will store the data, these two attributes, on the object for you, so you can pull it out and use it later. Gravity, don't worry about substeps and simulation speed just yet. And then you've got master start frame. Whether you want to use a master start frame, this will override what's going on in the source particles. And label point ID is kind of important. So and it's important for later, it's not greatly important for now. So if I put a watch point here, there's nothing existing right now because the particles have not started emitting. As soon as I go there, I get some data, which is what I wanted. And you can see here, this is a point ID attribute, 20 elements, and we have 20 elements. We have 20 particles right now. Point ID will be numbering these. So let's really, really quickly set something up. So if I go here and ID, and we'll do point scope off up in the corner here. Grab that guy, just so we can still see the particle. So we'll just make that a cube. Drop, I'll do a first in array. Cool. That's all good. And then we can come down here and say, go numeric and plug this into, plug this into there as well. And you can see, let's just change our point scope to be point. You can see these numbers. Each one of these is the particle's ID. So you can grab particle 54 later on, pull it out of the hat until it dies and do stuff to it. Particle 401, particle 435. Really, really important for when you're using data later on. When you've done your simulation looks good, but you want to do things to your individual particles. You have an ID there to do that too. What we're going to do now is we're just going to add an influence. What I'm going to put in here is a drag influence. So let's just play it and take a look. So this is what our particles are doing right now. I should probably turn off spin on collision, just to keep things fast and easy. There we go. There's our particles right now. So let's add a drag influence. That goes into the influences. And it's going to simulate air drag for us. Okay, so now that I've got that plugged in, we'll just play this. And you see how the particles eventually slow to a stop, because the air drag is overwhelming them. If I turn that off, we're back to what we had. Now I want to introduce you to modulate influence, which it allows you to scale the amount of the influence coming into it based on a property. So if I pop that into there, pop this guy, like replace the drag influence with this guy, which is cool. So, and we go here, and this is the property that it's going to use to modulate. So we'll change that to point age. And pretty much just change this to 0.5 and 1. So basically what's going to happen here is the drag force is going to increase as the particle ages. So let's have a look. Come out fast, and then they're slowing right down as the particles get older and older and older. Now that's a modulate influence. That's a very handy thing to get your head around there. And you can see our point age there and our point AD. So we can make all kinds of adjustments that we want here. Like maybe the maximum should be 0.5 and the minimum should be 0.1. Just to get a bit more of a other way around maybe. It's back to where we were. If I hit invert there, it'll swap to 2 and it'll stop much faster. Now we've got them evolving a little slower by setting the minimum to 0 and the maximum to 0.4. If I take that maximum up to say 0.8, you can see them, they're not ever completely stopping, but the drag ramps up fairly quickly and they just move very slowly. And we'll go with something like that for now. Now you can also do this after the fact. So because I have the point age here, I can set, let's say, the particle's size by the point age. So we'll go get geo property, and this is going to be the point age. We're going to get the point age. We need to check what sort of property point age is, and it's a float. So that's nice and easy. We can just pull this down to array float. We've got the point age. Then we can do our old friend, array bounds, and change range. Again, I keep saying we should turn this into its own compound. Plug the data into both of them. We'll plug the minimum bound into from start, the maximum bound into from end, and then we're free to change our new setting to whatever we like. So maybe I want them to start at 2 and end at 0.1. Then I can come along here and just really quickly set geo property. That's going to be the point size. Pop that guy into there. Just drop this over, geometry. And we need to restart the solver. So we're going to start really big. That's probably too big. So we can actually adjust this. So let's go 0.2 to 0.001 and play that. So you can see the particles getting smaller and smaller as they get older. They're still a little too big to start, so 0.1 maybe. That's better. So what you're seeing here is the particles scaling down as they get older. And of course then if you wanted to, I'm just going to change this back to sphere from cube. Like that. Let's go up to our source particles and change our particle size to 0.025 so that they're overall quite a lot smaller. And there we go. So we've got particles that are shrinking as they age. That's great. That's what we wanted to do. Let's do another one. Let's set the color of the particle based on its velocity. So again, get geo property. This time we're going to get point velocity. And velocity is a float 3. And what I'm going to do here is I'm just going to normalize it. So it's that converts it to between 0 to 1. I'm just going to pop this straight out to the emission color. And of course, to get the right data, we'll need to restart the solver again. Yes, you can see the particles change color based on their velocity. So just to finish this up really quickly, I'm going to get, well, it's not finishing up. So let's just make a few quick adjustments to make this look a bit better. I'm going to take my drag influence and I'm going to take that down to 2.5. So the modulate influence works in percentages. This is just going to move everything a bit faster. It's not as much drag on it. The modulate influence is just scaling that, whatever's coming into it. So that's the first thing I want to do. And I think we've got a little too many points right now. So let's change that back to count and we'll take our rate to 10. See what we're getting. That's a little more easy to read. Let's work on the collider settings. So let's go back and talk about that. So let's add another collider. So I'm just going to put a mesh plane down. Like that. And I'm going to pop it into our terminal so I can see what's going on with it. There it is. And let me just get this set up really quickly in the right place for us. I've just set up an external collider here, but I haven't hooked anything up yet. So let's make it a little more interesting. I'm going to take this plane, I'm going to displace it. I'm going to use our old friend, fractal noise field. Put that into the displacement. Let's take a look at what this is doing. And there we go. We've got a, let's just go two-sided lighting so we can see it better. There we go. We've got a bit of a fractally displaced noise. That might be just a little too detailed right now, so we'll take a number of frequencies down to 1. It's more like it, and let's just pop out magnitude a wee bit, and maybe just change the frequency a bit. So we've got this interesting looking wall here. Let's make it a little more interesting. Take that guy and let's just give it a bit on the y-axis, so it's not quite straight up and down. So it just looks a little bit like that from the side. This is going to become our new collider. And we can start working on the collider settings from that. Where's our collider? Our collider is here. You see in the collider, I'll just move these guys out a bit so we can get a closer look at them without getting too confused. Collider here, this is a fan import, which means I can put many, many things into it. So I'm just going to put this guy in here as well, reset that. I'm going to break the connection to the terminal and press play. And you can see the particles here are bouncing off that. So let's go into our collider settings and see what we can do about that. So looking at our collider, we've got enable. The method is automatic. For us, it's mesh for points. We're just going to use mesh, start frame, end frame, that kind of thing. Then common property. So detail size is how detailed the collider is. Offset means you can offset the collision. And inherent velocity, we'll get back on that in a minute. So this is for volume colliders. Let's double check the info here. These settings apply to volume-based collisions. These are not volume-based collisions. But what we really want to look at is down the bottom here is how bouncy, how much friction, how rough, and how sticky our collider is. Okay, because these all mean different things. Bounciness is pretty much what you think it is. It's how much velocity is conserved after it hits something and bounces off. So if this is a high number, all of at this point in time, all of the incoming velocity is preserved for the outcoming velocity, which means that what happens is this will fly off, hit the collider, and the reflected vector will be exactly the same magnitude as the incoming vector. So I don't want it to bounce. I just want it to be sort of sticky. Friction is how much motion it loses when it hits the collider. It's like an object-based drag. Okay. Roughness is how rough the surface is. Now this is just going to simulate roughness, but if you imagine a completely smooth pane of glass bouncing a ball on it, you know which way that ball's going to come off because it's the reflected vector on the direction that it hits the glass. But if you throw something against a lumpy, bumpy piece of concrete, then you're not quite sure which way it's going to bounce off. That's what roughness is. It's faking how rough the surface is. I'm going to add no roughness, is fine. And stickiness is how well things stick to the surface. Let's set up a bit of that and let's see what that looks like. And you can see our particles are changing color because their velocities are what's driving their color. So they're hitting the wall And they're still moving very slowly. Look here. And this is what these settings will do. They're not bouncing off. They're losing about half of their velocity every step through friction. The wall isn't rough at all. It's very smooth. And it's sticking to the wall by about 20%. So I'm just going to pause the video now and make you a really quick play blast so we can see that in real time and get a better idea. So here's what it looks like playing back in real time. And you can see the particles hit the collider, but they're still moving along it. Some of them stop dead. Other ones just keep moving along. That's what our collider settings have got for us. So have a play with that. See what you can make out of it. A good challenge would be to see if you could make them dribble down the wall. Obey gravity after they hit the wall rather than any other time. And of course, another good thing to do is let's take these influences out altogether so we're not changing the velocity of the particles at all. Play that back. So now they've got the particles coming out. Give them a much longer lifespan or even live forever. And simulate an awful lot more of them. So again, I'm going to pause the video and play blast this. So where I come from, we call this a Technicolor yawn. But beside that, you can see what it's doing. I've stopped the particles. I've made a few adjustments. I've stopped the particles emitting at a certain point. I think it's 100 frames by using the end frame, as you can see here. I've also changed the rate of the particles and a couple of other things that we've already been through. But what you can see happening here is, just close that, the particles are taking the shape of the colliding wall. If I turn on the colliding wall, which is this guy, plug him back in, turn him on, you can see that the particles are colliding and sticking, but still moving a little bit. So yeah, that's really the basics of creating particles. There are obviously a lot more things you can do. You can have them die on collision. You can have them spawn new particles when they hit something. You can have them split into two particles at a certain time in their life. You can do all kinds of stuff. Particles are great, and you get an ultra amount of control using particles to do things, which is superb. So the last thing we're going to talk about with particles is something that's going to stick with us for this whole lesson. It's really an industry-wide standard. Okay, we're going to talk about caching our particles. Let's really quickly talk about caching. So if I have, I don't know any studio that would accept this as final, unless it's for a very specific thing. But let's say I've finalized it, I've got approval, everybody's happy, we're ready to go out. Every time you want to use these particles, you don't want to generate them again and again and again once they're signed off and final. What you want to do is make a cache out of them. And what a cache is going to do is it's going to save each particle to disk. It's going to save its position, its color, its whatever you've got set up on your particles in terms of properties. It's going to save all of these to disk, especially if you're making particles to emit something else, so to drive aero or to drive maybe a point, you're doing some point cloud operations or something like that. So you really don't want to be generating these every single time you need to do something else with whatever happens after them. So what we're going to do is cache them out to disk. And the way we're going to do that is with a file cache node. Now, a file cache node is pretty cool. It allows you to cache things to Alembic, OpenVDB, and a Bob file. What a Bob file is Bifrost's internal format. So here's where I can plug this in, and I've got a mode here. I've got lazy, read, write, or pass through. If I choose pass through, and we'll just use our first object out, that cache is not going to do anything. It's just going to pass it straight through. It's still going to generate, you can tell by the speed and that kind of thing. Pass through is simple. It's what if you wanted to set up your graph with a cache included, because you're going to cache it later, you'd set it to pass through until you were ready to cache. When you're ready to cache, you've got two options: lazy mode, and if we check the help here, what this says is switches between read and write mode depending on whether or not a frame exists on disk. This mode can be used as a scrubbable, resumable cache. So let's give it a file name, and there's some rules around this. So I'm going to put this into my projects directory. Default, I've got a cache here and a Bob cache. See, I've been doing stuff in here before. But what I'm going to do now is I'm going to say particle exercise dot hash 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 dot Bob. What this is doing is this is the name of the cache, particle X. The 4 hashes are the file name extension, like you can see here. This is a standard exercise, this is the particle exercise. They're the frame number. So this is the cache for standard exercise for frame 11. Bob is the file format. Save as type object Bob. So we just hit save. We're on lazy mode and we're on frame 0. So if I navigate to that cache folder, there it is. That was just cached. You can tell what time I was doing this video and everything. But it's the first file, which is great. So now all we have to do is make sure we're not looping. So we just want to play through the timeline once. We've got our file name set up. The file cache node knows what it's doing because there's a Bob at the end of that. If it had been an ABC, we could use the Alembic. If it had been a volume, we could cache to an OpenVDB, which we'll be doing quite a bit of next week. But for now, we're just going to cache this to a Bob. So set that to write mode just to be sure. That is absolutely going to write on disk every single time. And I'm going to press play and pause the video and I'll come back when it's finished. Now what you do now, you've got your cache on disk. You can check it by looking at the folder that you cache to. There's all my particles. There's 300 and there's all the other ones going down. You can check the file sizes to make sure that it's actually put something out to disk. Switch the cache over to read mode. And now it's just going to read that cache off disk. And what you'll notice straight away is that it's a lot faster because it's no longer calculating the position of each particle. In fact, I can, if I want to, break that connection. So I'm just loading a file cache now. And there we go. They're all sticking and doing their things. And if we take a look at the data coming off the cache, you can see that all of my particle properties are still there. Bounciness, color, ID, all of that kind of thing. This is a really good habit to get into, not just because in any studio you work in, it's going to save you time, but because if you're trying to come up with an effect, so you may not be taking these particles into a game engine, but you might be driving something with them that you are going to take into a game engine. Some instances maybe, or a aero simulation or something. We don't know. Infinitely creative, that's the nice thing. Now you've got it to a point where you can scrub it. You can't do that when you're generating. Scrub along the timeline. You can play it back in real time. And then if I wanted to say add something to this, so if I go create instances, pop that out to the instances, and we'll just use a simple cube. Bring that out to the terminal. You can see that it's just instance to cube on every particle, and it's running nice and fast, and my cubes are nicely sticking to my collider there. You can see they're still shrinking as they get older. Some of them are still moving around. It's got all of the properties of the particles. I'm just applying it to an instance situation. So yeah, so that's basic particles. We're going to now move on to aero. Okay, so here's where we left our particles, and we're going to leave them alone now, because this is a good basic setup for particles, and it's going to help you moving on to what we're going to do now, which is some smoke. So let's drop these guys in a group. Oops, that was hide. Let's drop these guys in a group, call them particles, and hide them. And we'll close the Bifrost as well. So let's make a new graph.